Okay, welcome back. So we're moving on to section 17.2. It's really short in the book. It basically is just a collection of bullet points. So I'll also be linking, my videos for my ODEs course, which you've already seen a few of, because I touch on the same sort of ideas. These ideas of function spaces aren't really escapable once you get to a certain level in math. So I'll link over to the ODEs book and videos that I have, and so you can learn a little bit more about function spaces there. But let's just talk really quick. What are function spaces? Function spaces are vector spaces, which, and I don't think you really got too much into the exact definition of what it means to be a vector space, but a vector space just means that if I take two vectors, x1 and x2, these are just objects that we call vectors. Okay, so we give these the name vectors. And a vector space is just any collection of vectors which have the property that if I multiply them by a scalar, each respectively, right, a and b can be complex numbers. So if I multiply just two things, they're just objects, if I multiply those by complex numbers and add them together, I recover a third object. Whatever I'm considering my set of vectors, if I'm allowed to multiply them by a complex number and add them together, and if that gives me another vector, then that's called a vector space. And why is this kind of cool when it comes to functions is that we'll start to see, or even right now, if I consider two functions, rather than considering this x1 and this x2 as vectors, if I consider two functions, f of x and g of x, well, let's multiply them by complex numbers. Let's let a be some complex number and b be some complex number, and add those functions together. Is that equal to a third function? I think everybody agrees that yes, that's equal to a third function. In some ways, this function h is getting defined as the sum of the previous two, but that is a function of x. If I plug something into what I'm naming h, then I get a number out, and so that's another function. So since functions satisfy this property, I'll put it in quotes, property of vector spaces. So since functions satisfy that property, functions are vectors. And that's an interesting thing to think about, right? We don't traditionally perceive functions as vectors, and yet they are, because as mathematicians, the only requirements we make of vector spaces are exactly what I've written down for all of you, and that's just that if I take two elements, multiply them by complex, technically, or real numbers, or any other element of a field, but if I multiply them by something and add them together, I get another element of this space. That's all we're really requiring out of vectors. I mean, the mathematicians require more than that because we like to be pedantic, but definitely in a chemistry course like this is what we want to think. Any mathematical objects which we can multiply by complex numbers and add together to gain a new mathematical object which has the same structure as the originals, that's what a vector space is. And so function spaces are just, erase that, function spaces are also known as vector spaces of functions. That's what it means to be a function space, a vector space of functions. Now, why do we specify function spaces? In vector spaces, there was a difference between R3 and R2 and R, and all of those were vector spaces. And so when it comes to function spaces, you also have to be specific. You have to say, hey, I'm allowing myself a collection of functions with specific properties, but not just any function in the entire world, right? There are some functions I want to exclude from kind of the vector space I'm considering. And this is where we get into the definitions down here, or maybe some examples of vector spaces, and or function spaces, and that's that. So we place restrictions. I'll say to define a function space, we place restrictions, as in adjectives, on the functions we consider. So this is similar to just saying, I'm considering all vectors which are the span of 1, 2, 3 and negative 1, 2, 3. That's technically a perfectly valid vector space, and it's a subset of R3, but it's not neither R3 nor R2. It's like its own thing, and we do the same thing with function spaces by adding these adjectives. So one collection is the set of continuous functions is a function space or a vector space of functions, because if we add two continuous functions together, we recover a continuous function. Note here that the author is calling an interval of length L the set omega, which is the domain of the functions we consider. So in this specific case, we're considering functions with a particular domain of omega. So this set of continuous functions, you don't need to know this, but this gets defined as C of omega. C for continuous for obvious reasons. The set of differentiable functions, which is the next possible choice that we can be given, whose derivatives are also continuous. This is often denoted as C superscript 1 or C to the 1 of omega. The superscript there just says how many derivatives am I allowed to take. And if you'll remember, being a derivative is a subset. It's more specific than being continuous. You have to be continuous to be differentiable, but you don't have to be differentiable to be continuous. And so in some ways you can think about this as a subspace of this. So the derivatives or the differentiable functions are a subspace of the continuous functions. The same way that the span of 1, 2, 3 and negative 1, 2, 3 is a subspace of R3. So we start to be able to talk about subspaces as well, which is pretty cool. And actually the next one becomes a subspace of the previous two. If I'm considering analytic functions, they need to have a radius of convergence of at least L, I guess, but if I consider the space of analytic functions, I don't know the traditional notation for this, but I usually use an A for analytic. And then I'll say it's analytic on omega. That just means at every point in omega I have a convergent Taylor series. And that would be a subspace of the above, which itself is a subspace of the continuous functions. And so these are kind of cool. We can just talk about these as themselves as sets, which are contained in bigger sets, and each one is respectively a vector space. The next one is pretty common, especially for physicists. This is the classic, this is the physicists' favorite space. It is the most generic Hilbert space. And I mentioned briefly in the previous videos about Hilbert spaces being inner product spaces in infinite dimensions. This is the most generic Hilbert space. We call this capital L2 of omega. So I guess the set of functions with that property. So we call this L2. If anybody ever talks about L2 or L2 of omega or something, they'll usually just call it L2. Think in your head that is a Hilbert space in the sense that it's a vector space of functions, and it has an inner product on it, and a norm, in fact, right? So the norm, we're kind of defining the norm here as well. But these are the functions which once you take their norm of the function of the magnitude of the function, you square it. So this is the magnitude of my function, I've squared it, and then I'm trying to integrate that over a region. That's my L2, capital L2 set of functions. So let's just really briefly say, okay, 1 divided by the square root of x is not in L2 of 0L in this case, since the integral 0 to L of 1 over root x squared dx equals the integral of 1 over x dx, still from 0 to L, equals the natural log, right, of x at 0 and L, which is perfectly well defined at L. It's the log of L, but the log of 0, you'll recall, especially if you plug it into your calculator, that's infinity. With a negative sign in front of it, then it's infinity. So since that's infinity, that's saying that it needs to be finite. And since it's not finite here, if I actually try to compute it, it's not finite. That means that this is not an L2. So this is why the whole L2 is actually a restriction on the functions that we consider. If I had considered something instead like, which is really close, 1 over the cube root of x is in L2, 0 to L, because I can compute 1 over the cube root of x squared dx, 0 to L, I recover 1 over x to the 2/3 power dx with an antiderivative. That is, I guess, x to the 1/3 divided by 1/3 at 0 and L, and so I'll get 3 L to the 1/3 minus 0. And that is definitely a finite number. So just changing that little square root to a cube root, all of a sudden I gain something in L2 versus not being in L2. So this is where we have to be a little bit more specific about which functions are actually in these spaces. The top three is really kind of most of the functions we consider sit inside of these top three. But when you run into L2, you're getting into touchy territory where you actually have to start computing some integrals to see if a function is in there. And then the next two are just referring to the fact that, if I just highlight those as a total, this is referring to the fact that the set of solutions to a linear differential equation is a vector space, vector function space. So you gain a function space when you consider the set of solutions, which is also, aka the general solution. So the general solution is a massive vector space. That's why those unknown constants C1 and C2, those are basically the span. You're considering the span of whatever those are multiplying. The same way if I spanned 1, 2, 3 and negative 1, 2, 3, to compute the span of that, I just put constants in front of both of them and add them together. It's like a general solution. So the general solution basically is a vector or function space to a linear differential equation, and then a particular solution is a single element in that vector space. So that's what the last two are kind of referring to. Is that this is really kind of the reason why function spaces are used so commonly, because linear differential equations kind of describe our future to a certain extent. And so since the general solutions to what describes our future are function spaces, we care a lot about those. That's all I have for today, except for the other video that I'll share. So I'll see you in class. Thanks for sticking with me.